The stranger entered quietly, without spectacle, without warning, sliding across the outer dark of the solar system with a motion that seemed almost rehearsed. It was not the first time an object from another star had brushed past humanity's small celestial stage, but there was something undeniably different in the way this one revealed itself. Long before the instruments registered its formal designation, long before researchers debated its composition or its improbable behavior, its presence carried a tone, an ancient drifting whisper from interstellar night. It moved through space like a memory crossing a dream, its path neither erratic nor perfectly smooth, but imbued with a sense of long travel, as though shaped by epochs of stellar winds and forgotten cosmic collisions. For decades, astronomers had imagined such wanderers, fragments of shattered worlds, frozen relics of distant suns, the cosmic dustings of planetary birth and death drifting between constellations. The universe was old and violent after all, and the ejected remnants of alien systems should have been plentiful. Yet only in recent years did humanity truly begin to notice them. Oumuamua had been the first messenger, a flash of geometric strangeness that sliced past Earth with the indifference of a stone thrown across a pond. Borisov followed a more classical comet, yet still a visitor from far-flung origins. And then, as though responding to a cosmic rhythm, there came another, 3I Atlas. Even the name carried a quiet tension. The third confirmed interstellar object, the newest addition to a still-forming lineage of mysteries. But where its predecessors raised questions, this one raised alarms. It behaved not simply like something unfamiliar, but like something that refused the templates into which astronomers tried to place it. And from the moment NASA released the full mosaic of its first images, the scientific community felt the same uneasy pressure the story they thought they were reading was not the story unfolding before them. What arrived in those early frames was not a standard comet. It was not a shard of frozen gas and dust coated in the brittle crusts, typical of long-dormant wanderers. Instead, telescopes caught the outline of a smooth, luminous structure, a tear-shaped envelope of bluish haze encasing a core that glowed with a steadiness few had the vocabulary to describe. Not chaotic, not turbulent, not the wild plume of an object bursting awake in the warmth of a new star. It was something else, something measured, something strangely serene. Far out in the solar system, where sunlight is thin and the cold is ancient, comets typically sleep. Their surfaces remain dark and inert, the ice is buried within them, locked into silence, until the heat of a closer orbit begins its predictable transformation. But this object did not wait. It began to shed material at a distance where even the most volatile compounds should have remained frozen in place. The outgassing appeared smooth, almost uniform, as if emerging from beneath a hardened carapace shaped not by randomness but by consistency. In those first images released by NASA, images captured from multiple vantage points by observatories scattered across Scarlet Mars and the dim outer regions, researchers noted what should not have been possible, a cocoon brighter and more symmetrical than any known local analogue. And so the stranger arrived not merely as a visitor but as a contradiction. The solar system has long been a place of patterns where the behaviour of objects follows a language learned from centuries of celestial mechanics. Comets grow luminous tails that flare outward from the sun. Their shells fracture their jets, erupt in fits and pulses. Their orbits shift predictably under the laws of gravity dance beneath the tug of planets, and arc along trajectories shaped by the same Newtonian elegance that governs every rock and fragment under the sun's command. But 3I Atlas seemed immune to those expectations. It presented a shape without analogy, too orderly to be natural, too irregular to be controlled, too luminous to be dormant, too distant to be awake, and the silence of its approach only deepened the intrigue. No dramatic spectacle heralded its crossing of the heliopause, no cascade of radio noise or anomalous heat signature betrayed its nature. Instead, it drifted inward with the quiet confidence of something that had travelled for millions of years, and did not fear the scrutiny of a young species just beginning to understand the cosmos around it. For the researchers who first examined NASA's early gallery, the feeling was immediate and unspoken. This object was not simply unexpected. It was unprecedented. Over the following days, more images arrived. Files from Hubble revealed the elegant symmetry of its outer veil. Ultraviolet scanners detected hydrogen clouds where none should exist. Infrared lenses found warmth without sunlight to explain it. And deep space probes reported angles deviations, and flickers of motion that hinted at forces working beneath the surface forces that did not align neatly with any familiar model. Yet before the scientific shock took hold, before theories expanded to fill the growing void of understanding, there was this opening moment, a silent arrival, a stranger drifting into the domain of the sun, carrying with it the layered scars of interstellar history. Nothing about its approach announced danger, but everything about its form suggested a complexity that demanded attention. It evoked the same unease that accompanies the discovery of a language with no Rosetta Stone, a structure whose meaning exists but lies beyond immediate interpretation. Among astronomers, a certain reverence permeated those first discussions. An interstellar object is not merely a piece of rock, it is a time capsule. It carries within it the chemistry of alien worlds, the fingerprints of distant stars, the echoes of gravitational battles fought in systems humans will never see. It is matter shaped by experiences foreign to this solar system's quiet spirals. And now suspended in the black, this traveller's unusual form reflected the sum of those experiences across its hardened shell. No two interstellar objects should be identical, yet none should be so distinctly singular. As the first section of the narrative closes, the image of 3i Atlas hangs like a lantern in the dark, a glowing cocoon suspended between worlds shimmering with clues that ask more questions than they answer. It is the calm before the deeper storm of discovery, a moment when the object is still just an object, a visitor barely understood, a whisper at the edge of comprehension, but soon the solar system's full attention will turn toward it. Soon 15 spacecraft will align their instruments like a cosmic audience, listening for the first note of a long-anticipated symphony. And soon the stranger will cease to be silent. The moment the object's strange luminosity spread across the first composite frames, something shifted within NASA's silent hallways and digital workrooms. There are discoveries that excite, and there are discoveries that unsettle even before their details are understood. 3i Atlas belonged firmly to the latter category. Within hours of the first processed observations, the subtle alarm was transmitted through private channels, internal memos, and late-night teleconferences. Not panic. NASA does not panic, but an unmistakable consensus that something unprecedented had crossed the sun's domain. The decision that followed was as swift as it was historic. 15 spacecraft, widely dispersed across the solar system, each with its own mission, its own schedule, and its own constraints, were asked to redirect their gaze toward a single wandering object. This was not routine. Not even extraordinary objects receive such attention. When a distant body is discovered, 1 or 2 observatories may pivot for supplemental observations. Sometimes 3, but never 15. Never a coordinated, synchronized network stretching from Earth's orbit to Mars, from the inner heliosphere to deep space probes that had no reason to look back. The participating fleet formed a kind of technological constellation, a distributed nervous system capable of observing in light heat, ultraviolet radio, and gravitational nuance. Each spacecraft was a node in a vast lattice of perception, and each was suddenly asked to pause its long-planned experiments to peer at the same intruder drifting through the void. The reasoning behind this decision was straightforward yet profoundly symbolic. Interstellar objects are rare, so rare that before Oumuamua none were known, and while Borisov suggested such visitors might be more common than once believed, their fleeting trajectories still allow so little time for scientific scrutiny. When one enters the solar system, it does so like a stone entering a lake, briefly, silently, and irreversibly. If humanity wishes to understand such a messenger, there is only a narrow window, a few months, sometimes less. But rarity alone could not justify the enormous retasking NASA approved. It was the differences, the immediate measurable differences, that ignited the need for a comprehensive multi-instrument response. Those first images hinted at alien chemistry, unfamiliar morphology and behaviour that flickered at the periphery of expectation. This object was not simply a visitor. It was a challenge directed not toward human imagination but toward physics itself. And so NASA acted. The call went out to the Hubble Space Telescope, still orbiting steadfastly above Earth. Despite its age, Hubble's ability to capture high-resolution morphology made it the first guardian of visible structure. The request arrived: direct your lens toward 3i Atlas. Record its form, map the luminous cocoon, observe its evolving brightness. Hubble complied with calm efficiency, its instruments turning toward the anomalous glow. James Webb, positioned beyond the moon, received the next message. Its infrared capabilities made it uniquely suited to detect the elemental signatures hidden beneath the dust. JWST's role would be to identify the chemistry of the gases, the volatiles, the thermal gradients that radiated from a nucleus still unmodelled. Webb adjusted its schedule, opening its eye to the cold visitor. Meanwhile, MAVEN, circling Mars, was asked to perform ultraviolet scans to detect hydrogen signatures. Its data would reveal whether water, the most fragile of cosmic molecules, was present in quantities large enough to shape the object's halo. The result would later shock the scientific world, but at this early moment, MAVEN simply adjusted its orbit and began gathering photons. The Mars Reconnaissance Orbiter, equipped with its powerful high-rise imager, received its instructions next. Standing watch from the red planet's orbit, it was tasked with capturing the dust envelope at resolutions no Earth-based observatory could match. Perseverance, stationed on the Martian surface, was instructed to watch the distant sky. Even a faint point of light could reveal ecologically significant dust properties when observed under the planet's thin atmosphere. Then came the deeper probes, Psyche and others positioned far from Earth, each scheduled to study separate planetary relics. Deep space is not a convenient environment for opportunistic astronomy, yet the anomalous nature of the object justified the shift. Lucy's vantage point beyond Earth's orbit provided angle and reflectivity data no other platform could supply. Psyche's starfield tracking could detect deviations, subtle, almost imperceptible shifts hinting at non-gravitational acceleration. Solar-facing missions were added next. Punch would attempt to observe solar-wind interactions. SOHO and Stereo, both sun-monitoring spacecraft, would search for visible spectrum behavior, though the results would later contradict nearly all other observations. Parker Solar Probe, racing close to the Sun, was requested to identify any solar-driven anomalies in dust tail formation or ionization fronts. Europa Clipper, still in its pre-primary mission phase, added long-range imaging from its vantage point near the Jovian system. Even its limited survey capacity could capture scattering signatures of the dust cloud. Piece by piece the network formed. No single instrument, no matter how sophisticated, could capture the full identity of an interstellar object, behaving in ways that stretched the limits of cometary physics. Only by collecting data across wavelengths, distances and geometries could a coherent image eventually emerge. What made the moment historic was not the number of spacecraft, though 15 was unprecedented, but the unity of purpose. Each observatory possessed a unique lens, infrared, ultraviolet, visual, thermal, spectroscopic. And yet all were now oriented toward one drifting point in the void. In effect, NASA created a distributed observatory, spanning the solar system, a kind of artificial super telescope stitched together through mathematics and the silent cooperation of distant machines. Behind the scenes, scientists navigated pressure and excitement in equal measure. The immediacy of the data demanded long work nights, cross-disciplinary communication, and the rapid reframing of existing comet models. Interstellar objects had always held a whisper of the unknown, but this one carried the tonal weight of something more profound. Not because it hinted at artificiality, though the thought arose in quiet corners, but because it challenged the boundaries within which natural physics usually operates. The observing campaign became not merely a study, but a reckoning. In the conference calls that followed, researchers compared initial results. The smoothness of the cocoon, the asymmetry of dust distribution, the early signs of water release. They spoke in careful, measured sentences, aware that their words were being transcribed for future review. Scientific excitement is powerful, but it must be disciplined. At this early stage, discipline was a shield against speculation. Yet beneath the professionalism, a human truth lingered. They were watching something no one had ever seen before. Something that might echo the earliest formations of alien systems. Something that could transform the understanding of cosmic chemistry and cometary evolution. Something that might force a rewriting of textbooks, research proposals, hypotheses. Something that had travelled for millions of years only to reveal its strange identity now here in the fragile cradle of the solar system. As the 15 spacecraft aligned their gaze upon the incoming visitor, a sense of collective anticipation spread across the scientific world. The stage was set. The instruments were calibrated. The mission, though improvised, was precise. The solar system had turned its eyes toward the stranger, and the stranger was about to answer. The first wave of images arrived like an unexpected whisper, quiet, unassuming, but carrying within them the seeds of profound disruption. Researchers who opened the early Hubble files expected graininess, irregularity, the rough edges typical of a distant comet just beginning to make itself known. Instead, what glowed on the screens was an object that refused to follow any familiar script. It did not erupt with chaotic plumes or scatter sunlight in erratic flickers. It did not display the rough, craggy silhouette of a nucleus awakening under solar heat. What the images revealed was something smoother, more symmetrical, more strangely deliberate. The luminous cocoon surrounding the object showed no sign of the triangular directional tail seen in ordinary comets. Instead, it resembled a teardrop softly curved, perfectly tapered, and enveloping the core in a bluish haze that seemed almost sculpted. To the scientists who had spent careers studying frozen wanderers, these features were subtle but deeply unsettling. No comet behaves with such uniformity. No comet releases dust in a manner so controlled, even so resistant to the uneven forces of sunlight and solar wind. In the dimly lit observation rooms, experts leaned closer to their screens. They zoomed in, adjusted contrast, studied the grain-by-grain distribution of dust. What they found was a morphology that contradicted the very principles by which comets are understood. Natural outgassing is chaotic. It fractures surfaces, creates jets, carves pits, and scars across a nucleus. The resulting cloud is ragged, dispersed, and asymmetrical. But here, every pixel seemed to defy the familiar patterns. Within hours, the implication settled in: if this object's behavior was natural, then its natural environment must be unlike anything found in the solar system. More images arrived. MAVEN's ultraviolet scans added a second anomaly, a vast hydrogen halo encasing the object, far too large, too diffuse, and too active for a body still so distant from the sun. Hydrogen halos form when ultraviolet radiation splits water molecules into oxygen and hydrogen. But that process requires heat that should not yet exist. For a halo of this magnitude to appear at such a range was, in the most measured scientific terms, baffling. Teams ran simulations adjusting for every known variable. None fit. Even the Mars Reconnaissance Orbiter's high-rise instrument contributed to the growing confusion. From its vantage point, orbiting Mars MRO captured the object as a white semicircle suspended in darkness, its dust envelope thickest on one side, as though shaped by an uneven but persistent internal force. It was neither round nor elongated, but something in between, like a crescent shell illuminated from within. The strangeness deepened with each dataset. Punch revealed the tail angled sideways, defying physics that ordinarily forces comet tails to point directly away from the sun. Psyche detected minute deviations in trajectory, subtle yet unmistakable, suggesting non-gravitational acceleration similar to but not identical with the anomalies once associated with Oumuamua. Spherics observed a warm core. SOHO saw little more than a faint yellow dot. JWST found chemical offsets inconsistent with known comet materials. Nothing matched, nothing aligned, nothing behaved as textbooks predicted. In meeting rooms and digital channels, the tone shifted from curiosity to scientific unease. Not because the object hinted at artificiality. Scientists resist such leaps, but because it displayed patterns that contradicted the stability of existing models. When enough contradictions accumulate, the foundational principles must be questioned, not discarded, but re-examined under the weight of new evidence. For some astronomers, the earliest images felt like a return to the moment when the first deep-field photographs shattered assumptions about the size and composition of the universe. The emotional cadence was similar awe mixed with disorientation, intellectual thrill infused with the recognition that knowledge was evolving faster than the language used to describe it. In those early hours, one question emerged across the scientific landscape, whispered across research forums and late-night calls. What are we actually looking at? It was not the appearance alone that provoked the question. It was the coherence of the anomalies. Each inconsistency might have been dismissed if isolated, but together they formed a pattern that refused simplification, a smooth cocoon instead of chaotic outgassing, a hydrogen halo too large for solar distance, a tail defying solar wind orientation, a thermal core warmer than models allowed, a dust envelope shaped in ways no comet had displayed, a reflectivity spectrum inconsistent across instruments, a trajectory with slight inexplicable drift. Individually, each observation could be explained by edge-case physics, unusual compositions, or extreme origins. Together, they became a challenge. The scientific shock did not come from fear. It came from recognition that the solar system was not a fixed classroom where cosmic objects behaved predictably. It was a living stage, and something unknown had stepped upon it, wearing a shape that no textbook had prepared anyone to interpret. Early hypotheses surfaced cautiously woven with the restraint required by professional skepticism. Some suggested hypervolatiles trapped beneath an insulating crust. Others pointed to radiogenic heating, hydrogen-saturated ices, or unconventional mineral structures formed around exotic stars. More speculative discussions involved possible fragmentation of exomoons or relics of long-dead planetary systems far older than the Sun. Each idea carried weight, yet each faltered in the face of contradictions presented by the images. In the quiet corners of their minds, researchers felt the tremor that comes when a paradigm is about to shift, not because the object was dangerous, not because it broke rules maliciously, but because its very existence questioned the completeness of human understanding. The scientific shock, then, was not merely observational, it was philosophical. The universe had once again offered a puzzle carved from distance and time, a riddle whispered through dust and light. And as the early data settled into public and private archives, one truth became clear. The mystery of Three-Eye Atlas would not be resolved quickly. Instead, it would deepen one image at a time until the solar system's instruments revealed not only what the visitor was, but what humanity had not yet learned to see. The deeper the spacecraft peered into the drifting visitor, the more the mystery thickened into something textured, layered, and stubbornly resistant to interpretation. The opening anomalies, strange morphology, unusual brightness, and early hydrogen halo were only the first chords of a more complex symphony. Once the initial observations were processed and analysed, NASA and its partner institutions began the far more meticulous work of collecting additional data. Every instrument that could contribute was reassigned, recalibrated, and on some missions reprogrammed entirely to tease out the object's underlying nature. The data did not disappoint, it confounded. James Webb, positioned far beyond the Moon's orbit, trained its exquisite infrared gaze upon the interstellar body for a deeper pass. Webb's infrared spectrograph is one of the most sensitive tools ever built, capable of detecting molecular signatures in the faintest slivers of light. When those readings returned, they revealed the first chemical hints, and the hints were anything but ordinary. The spectrum showed water vapor as expected for any comet-like body beginning to shed ice. But embedded within those signatures were deviations, unexpected absorption features, minor yet persistent, that did not align cleanly with known ices, organics, or silicates common in local comets. They were not the fingerprints of a familiar solar system body. Instead, the object displayed a chemistry that seemed to reflect an origin forged beneath different starlight, in regions where pressures, temperatures, and radiation shaped matter in ways never observed nearby. Alongside Webb's data, SphereX contributed its own revelations. When the thermal signatures were compiled, a striking pattern emerged. The object's internal warmth was not distributed evenly. Instead of cooling uniformly as an inert comet drifts through the outer solar system, Three-Eye Atlas maintained a localized region of elevated temperature. A thermal pulse that stayed stable over multiple passes, as though something beneath the surface radiated heat, with gentle persistence. If it were merely sunlight absorption, the heat would reflect surface geometry, dark patches, bright patches, irregularities. But the temperature appeared to rise from deeper layers, hinting at internal processes. Not necessarily exotic radiogenic materials can warm even ancient comets, but the intensity and spread of the heat did not align with any single explanation. The internal temperature gradient raised questions about the object's structure. Was it layered, stratified, composed of compressed materials once subjected to intense cosmic environments? Meanwhile, ultraviolet data from MAVEN forced the scientific community to confront yet another puzzle. The enormous hydrogen halo, far too large for the object's distance from the Sun, was not merely an artifact of early imaging. Follow-up scans confirmed its size, density, and asymmetrical distribution. The halo fluctuated, growing and shrinking in intervals that suggested internal variation rather than consistent solar-driven sublimation. These fluctuations hinted at episodic releases, as if the object were venting from deep reservoirs beneath its crust in pulses rather than in continuous evaporation. For comets within the solar system, outgassing typically reflects surface ices transitioning into vapor. But this object did not behave like a fragile porous snowball. Instead, its release seemed regulated, almost buffered like gas escaping through fissures beneath a hardened layer, emerging in controlled surges rather than chaotic jets. MRO provided additional clues. Its high-resolution images captured a dust envelope that was not chaotic but softly shaped thicker, on one hemisphere thinner on the opposite. The asymmetry was striking and puzzling. Dust did not spread randomly. It followed gradients that should not exist unless the body itself possessed unusual compositional contrasts or had undergone heating patterns from environmental conditions no longer present. And then came data from Punch, a sideways tail, faint but distinct drifting at angles, inconsistent with the sun's influence. Rather than pointing cleanly away from our star as physics dictates, it hovered at an offset, a deviation small enough to require careful measurement, yet large enough to reject any simple explanation. Solar wind variability could account for some fluctuations, but not the persistent shift observed in multiple frames. The sideways tail implied either hidden forces acting within the object or an external influence yet to be identified. Meanwhile, deep space instruments like Psyche contributed precise astrometric measurements, tracking the object's position against star fields with exquisite accuracy. Over time, these measurements revealed tiny deviations in trajectory, minute accelerations, slight drifts. Nothing dramatic enough to provoke alarm, but enough to suggest that gravity alone was not the only force shaping its journey. The deviations echoed whispers from past mysteries. Oumuamua had exhibited similar behaviour, non-gravitational acceleration, that sparked debates still unresolved. Yet the similarities were not perfect. 3i Atlas drifted differently with a more subtle, gradual variability. A pattern that did not fit propulsion, but also did not entirely fit natural outgassing. Layer upon layer, the object revealed contradictions. The more scientists studied it, the more they found themselves navigating a landscape where every answer led to deeper uncertainties. It was as though the visitor had carried the imprint of a cosmic history, incompatible with local expectations, a relic sculpted by environments the solar system never experienced. And then, as the datasets multiplied, the anomalies began to form faint but recognizable patterns. Infrared data aligned with ultraviolet scans suggesting a compositional interior rich in volatile materials. Thermal signatures matched regions where dust appeared thicker, indicating structural layering. Reflectivity patterns from Lucy and Soho, though contradictory in isolation, hinted at complex scattering properties shaped by unusual grain sizes or mineral compositions. This was the heart of the deeper investigation, not the discovery of a shocking revelation, but the slow assembling of a mosaic still incomplete, but revealing fragments of an object far more intricate than the standard comet models could accommodate. Each observation, each wavelength, each angle, each scattered photon added depth to the mystery. Not chaos, but complexity. A complexity that hinted at ancient processes, long journeys and materials shaped beyond the sun's educational grasp. The deeper investigation did not answer the core questions. Instead, it refined them, clarified them, focused them into sharper, more resonant inquiries. What environment could create such a body? What forces could sculpt its crust into a smooth teardrop form? What internal processes could sustain warmth at such distances? What materials fracture in pulses instead of jets? What ancient stellar nursery birthed its chemistry? And most of all, how much of the universe's natural architecture remains invisible simply because humanity has never encountered it before? In this way, the deeper investigation did not resolve the mystery, it deepened it. With every photon captured, every heat map decoded, every spectral curve analysed, 3i Atlas revealed itself not as an anomaly, but as a window into a cosmic vocabulary that humanity had only begun to read. The deeper the scientific community ventured into the strange interior of the data, the more 3i Atlas revealed a pattern of behaviour that did not merely defy expectation, it intensified the mystery. What began as a constellation of anomalies soon coalesced into something more formidable, not a list of irregularities but an escalation, a crescendo of contradictions that seemed to unfold with deliberate rhythm. Each new dataset amplified the previous uncertainties, turning minor curiosities into deeply troubling inconsistencies. It was no longer a question of whether the object was unusual. It was a question of how far the strangeness extended, and whether the known laws of cometary physics were capable of containing it. As the object slipped closer to the inner solar system, its features sharpened. What appeared distant and diffuse in early images grew clearer, more structured, almost architectural. The smooth, teardrop cocoon captured by Hubble did not dissipate with increased solar radiation, as a normal comet's envelope would. Instead, the structure intensified, the outer halo thickening in a way that suggested layered outgassing rather than chaotic evaporation. But layered outgassing implied internal organization. An internal organisation implied processes that, if natural, belonged to origins far beyond familiar stellar environments. The hydrogen halo, already oversized, began to exhibit fluctuations that mapped into patterns. MAVEN detected rhythmic pulses of dissociation expanding and contracting, as though driven by internal oscillations. These were not explosive bursts of volatile release, the typical behaviour of comets nearing warmth, but soft, strangely periodic expansions. The pulses rose and fell in an almost biological cadence, though nothing alive was remotely implied. It was simply the inexplicable regularity that unsettled the data teams, a synchronization of chemical release that suggested internal structures regulating pressure, heat, or composition. No known solar system comet behaves this way. Their interiors are chaotic caverns of frozen ices, not layered chambers capable of coordinated behaviour. Then the tale shifted again. Punch, after its initial sideways tail discovery, continued monitoring the object across solar wind conditions. If the first observation could be attributed to transient fluctuations in solar wind direction, a localized anomaly, subsequent imaging should have corrected it. But instead of returning to a clean alignment away from the sun, the tail drifted even further off axis. There were moments when it partially aligned only to swing back into a position that made no physical sense. Solar wind variability could explain some of this, but not the persistent offset, not the repeated sideways curve, not the moments when the tail appeared to split at its point of origin, creating bifurcated angles that rotated as though influenced by internal momentum. The deeper the solar system looked, the more the object appeared to act as though the forces shaping it came from within, not from sunlight alone. And then came the brightness escalation. Lucy and JWST both recorded the same phenomenon from opposite sides of the solar system. The object's core brightened in the infrared spectrum not once, but repeatedly in pulses aligned with the ultraviolet halo expansions. The brightening was not explosive flare. It was gradual, smooth, and almost too elegant for natural sublimation processes. The warming, cooling, and rewarming cycle emerged, each phase lasting hours, then days, then returning in a way that suggested an internal feedback system at work. What mechanism could produce synchronized thermal and ultraviolet emissions at interstellar comet scales? No existing model could provide an answer. Even the dust envelope, the semicircular halo captured by MRO, shifted in shape over time. What began as a thickened hemisphere gradually evolved into a more symmetrical shell, then back into uneven distribution, as if the object rotated around an axis that did not match its visible brightness pattern. Dust transport models designed to simulate the influence of spin, sunlight, and gas release failed to replicate what MRO observed. The dust appeared to move as though responding to internal forces, not external ones. Scientists attempted to model a fractured exoplanet shard, perhaps the remnant of a shattered moon or ice giant. But such fragments carry chaotic surfaces, exposed materials, and irregular outgassing. None of these models matched the calm, controlled, and evolving cocoon surrounding 3I Atlas. Even Psyche's trajectory drift measurements escalated into something more worrisome. The initial deviations, barely perceptible, multiplied. Tiny accelerations increased. The shift remained non-gravitational, but its consistency strengthened. The drift was not random. It had directionality. Not propulsion, nothing so clean. But some asymmetric force repeatedly nudged the object in ways that could not be explained through typical cometary jets alone. And so, for the first time since the discovery, the question whispered in private forums gained clarity. Is the object in a stable natural state? Or in a transitional one? For if the object was transitioning, warming, shedding, pulsing, drifting, then the solar system might be witnessing not a static relic but an evolving phenomenon. A body changing as it entered a new stellar environment for the first time in eons. If so, every new observation was not merely a snapshot, but a chapter in an unfolding story written across millions of miles. The escalation continued as Webb performed its deepest spectroscopic pass yet. The results confirmed the earlier chemical deviations and added new ones, mineral signatures inconsistent with any body formed under the sun's radiation profile. Grains that scattered light with alien geometry. Volatiles that sublimated at temperatures too low for solar system materials. Structures within the dust envelope that suggested ancient cosmic bombardment under energies no longer present near Earth. As these results circulated through research groups, a phrase emerged quietly at first, then carefully woven into preliminary reports. Non-standard physics. It did not imply impossibility. It did not imply intelligence. It did not imply anything beyond the scope of nature's vastness. It simply meant what we see does not match what we know. The mystery deepened not through dramatic revelation, but through accumulation, each data point a layer added to a structure whose final form remained hidden. Looking at the growing archive, researchers realized that 3i Atlas was transforming into one of the most complex natural puzzles ever observed, a body shaped by environments different from the sun's evolving in real time. Its internal processes revealing themselves through faint pulses, drifting tails, shifting halos, and contradictory spectra. The escalation was not in violence nor in danger. It was in impossibility turned gradually, insistently into reality. As the object drifted inward and the flood of multiband data grew denser, the emerging picture of 3i Atlas began to fracture into something even stranger. Something more elaborate, more layered, more difficult to categorize within the familiar boundaries of comet science. What had at first appeared as a simple semicircular dust veil surrounding the nucleus slowly revealed itself to be a structure of remarkable complexity. And it was the Mars Reconnaissance Orbiter, with its cutting-edge high-rise optics, that provided the first undeniable visual clue. The earliest high-resolution frames delivered from MRO showed the object as a luminous arc suspended in darkness, a semicircle of dust so clearly defined it seemed artificially sharpened. Comets do not form arcs. They form diffuse envelopes, chaotic and unconfined. Yet the arc around 3i Atlas possessed a curvature that suggested internal cohesion, as though sculpted by forces emanating from within, rather than shaped by sunlight or solar wind. Grain density measured along the arc's edge displayed startling uniformity. The brightest segment lay not where the sun's heat was strongest, but along a region offset from expected thermal gradients. As more hours passed and more images accumulated, the arc expanded into what observers reluctantly described as a shell, a half-sphere of dust, thicker on one side, thinner on the other, moving with an internal logic foreign to any observed comet. The dust was neither blown cleanly away from the nucleus nor dispersed into the wake of the object's motion. Instead, it appeared suspended in a kind of dynamic equilibrium, as though caught between competing forces that held it in place. This shell was not static. Time-lapse sequences revealed shifting brightness along its rim, rippling faintly like a soft tide of particulate light. Rather than dissipating as the object warmed, the shell regenerated, thickened, then thinned again, cycling in subtle patterns. It behaved almost like a cloak part, insulation part, emission layer part unknown. Meanwhile, MRO's multispectral scans indicated that the dust grains themselves were unusually reflective in certain wavelengths and unexpectedly opaque in others. In ultraviolet, the shell glowed faintly, echoing MAVEN's detection of a vast hydrodynamic halo. In infrared, portions of the semicircle radiated heat more efficiently than surrounding regions. The grains appeared to be composed of unusual mineral blends, their scattering properties inconsistent with the grain sizes typical of solar system comets. This was the first sign of anisotropic heating temperature differences across the dust shell that could not be fully explained by sunlight angles alone. Something beneath the surface was warming one hemisphere more intensely, producing uneven dust release that nevertheless arranged itself in a structure of surprising symmetry. But the deeper shock followed soon after. When scientists overlaid the MRO imaging with early punch solar interaction data, they discovered that the faint sideways tail, already an extraordinary anomaly, originated precisely at the region where the shell grew thickest. The dust arc and the sideways tail were not separate phenomena. They were connected. The thickened arc was the origin point of the directional deviation. Comets typically develop tails based on the direction of solar wind. Their dust envelopes form independently shaped by sublimation and rotation. But this object showed correlation between shell thickness, heat distribution, and tail direction, an interlinked triad without precedent. Even more unsettling was the internal structure hinted at by spectral data pockets within the nucleus releasing material in deliberate pulses. MRO's readings suggested deep fractures or reservoirs that vented periodically, depositing dust into the semicircle with measured rhythm. This rhythm, faint though it was, echoed the thermal pulses detected by spherics and the ultraviolet fluctuations MAVEN observed. What emerged was a picture of layered behavior, one that defied the chaotic spontaneity of natural comet activity. This object seemed stratified, an inner core warming unpredictably, a mid-layer releasing gases in controlled bursts, and an outer crust resisting fragmentation with unexpected resilience. The dust shell then was neither explosion nor plume. It was the visible record of these internal layers interacting, shaping the dust cloud into a half-sphere. Other spacecraft contributed their own fragments of understanding. Perseverance's long-range observations from the Martian surface detected faint dust patterns that matched MRO's measurements, confirming that the semicircle's brightness was not an artifact of angle, but a genuine structural feature. Even from millions of kilometers away, the envelope shimmered with unnatural consistency. The object did not simply shed dust, it arranged it. The longer the shell was observed, the more its behavior contradicted known thermal models. In some frames, the semicircle extended smoothly behind the nucleus. In others, its brightest region rotated slightly independent of solar direction. The shell pulsed in faint radiance as though responding to internal cycles rather than external forces. It behaved almost like a boundary layer one formed by materials vaporizing from subsurface pockets, then cooled and shaped again by environmental shifts. In the inner solar system, such behavior might be attributed to rapid heating fractures or spin stability. But 3I Atlas remained too distant from the Sun for classical explanations. Nothing in its environment should have created a shell so dynamic, so structured, so coherent. As the data accumulated, scientists struggled to fit the observations into existing frameworks. The shell was too smooth to be coincidence, too organized to be chaos, too dynamic to be static. It reflected a history written in unfamiliar forces, perhaps sculpted under radiation from a very different star or shaped by temperatures and pressures no solar system body had ever endured. Some suggested it might be the relic of a differentiated object with layers formed by ancient heating events in a system older or more volatile than our own. Others proposed it could be the remnant of an exomoon shattered long ago, its interior composition blended and fused by pressures that no intact moon in our system has ever known. Whatever its origin, one truth became undeniable: the semicircle and the shell were not superficial oddities. They were signatures of a deeper structure, one that hinted at the object's birth, its journey, its transformations across light years of interstellar space. The shell was the first window into that deeper structure, a window through which scientists glimpsed both the complexity of the object and the complexity of the environments that created it. And with every new pass, every pixel sharpened, that window widened. As the semicircular shell took shape in the data streams, another phenomenon subtler at first, then increasingly impossible to ignore, began revealing itself. It was a gesture of defiance written in dust and sunlight, a quiet violation of celestial order. The tail of 3I Atlas, that faint and tenuous thread, usually governed with strict obedience by the sun's radiation pressure, refused to point where physics demanded it should. Instead of streaming cleanly away from the sun, it listed sideways, angled like a banner caught in a contrary wind that did not exist. The first images from Punch were almost dismissed. Solar wind turbulence can shift comet tails, slightly bending them, warping them, fraying their edges. But the angle captured in those early frames was sharper than expected, noticeable even before calibration. Analysts checked their orientation matrices. They checked instrument clock sync solar wind models, even the spacecraft's own pointing logs. But the angle held. And when follow-up images arrived hours later, the tail had shifted further, rotating away from the expected vector, as though resisting the directional push of sunlight. In typical comets, dust tails behave with mathematical simplicity. The particles energized by solar radiation are blown outward like smoke carried by a breeze. The direction is fixed by physics, not by whim. Dust points away from the sun. Ion tails point even more sharply. Deviations are temporary, always explainable, always grounded in the behavior of the star. But the tail of 3I Atlas was not a compliant plume. It drifted with an independence that grew more pronounced with each pass. The tail sometimes curved almost perpendicular to the solar direction. In other frames, it forked into two faint branches before recombining, and in the most baffling images, the tail arched slightly toward a region of the object's dust shell, the very region MRO had identified as thicker, denser, and warmer. Patterns were assembling. The tail pointed not away from the sun, but toward the locus of internal activity. This was not merely defiance, it was coherence. Punch's imaging sequences, constructed from hours of continuous observation, revealed that the tail's angle fluctuated in sync with the subtle pulses detected by MAVEN in the hydrogen halo. Every time the ultraviolet halo expanded those rhythmic breaths of dissociated water, the tail shifted slightly as though responding to internal dynamics, rather than external forces. Scientists began to split into interpretive camps. One group argued for solar wind anomalies. The The space between the Sun and the object could contain turbulent pockets, shifting currents of charged particles that might momentarily redirect a dust stream. And indeed, the Sun is no perfect engine. Its winds vary in speed-density direction. But these variations occur on large scales, affecting regions not carving precision paths through singular objects. Another group pointed to asymmetric outgassing. If the object emitted jets from within a fractured hemisphere, those jets might impart subtle thrusts nudging dust in unusual directions. Yet the dust patterns were too smooth, too coherent, too synchronized with ultraviolet fluctuations and thermal pulses to match the randomness of jet activity. Then there were the gravitational dynamics minute forces exerted by the object's rotation, mass distribution, or internal structure. But these could bend motion of the nucleus, not the orientation of a dust tail thrown outward into solar pressure. Gravity could shepherd particles close to the surface but not alter the entire tail's macroscopic direction. The sideways tail remained an unexplained gesture. Stereo's imagery added to the puzzle. Its vantage point allowed it to observe the tail's dim structure as faint vertical stripes, complex layers, oriented nearly perpendicular to what solar wind models predicted. These stripes were not merely shadows or imaging artifacts. They were bands within the dust itself, patterns carved by forces acting along the object's own axis of symmetry. It was as though the visitor carried its own internal compass, a directional preference written not by sunlight, but by its own deeper geometry. As scientists overlaid the tail direction across multiple spacecraft observations, mapping angles from Punch, Stereo, MRO, Lucy Perseverance, and even SOHO, they noticed something startling. The tail's deviations were not random. They rotated around the nucleus in slow, deliberate arcs following a periodicity aligned loosely with the object's inferred rotation period. It suggested the tail itself was anchored not to the Sun's direction, but to the internal structure of 3I Atlas. Many comets spin, many have jets that create subtle torques, but none exhibit dust behavior that aligns with internal rotational geometry rather than solar radiation physics. Here for the first time, the tail behaved almost like a signature of the object's inner workings, a tracer of motion of layered vents of deep-seated thermal forces acting through surface materials in ways no solar system body demonstrates. Scientists who worked on the Oumuamua anomaly felt a wave of recognition, yet also caution. That object had shown non-gravitational acceleration but no visible tail. Here the non-gravitational forces were subtler, but the dust revealed the story in luminous drifting clarity. Unlike Oumuamua, this object possessed visible mass shedding, but the shedding refused to obey the Sun. If Oumuamua broke the rules through absence, 3 Atlas broke them through presence. The sideways tail did not imply engines. It did not imply intention. Nothing in the data pointed toward artificial manipulation, but it did imply that the forces shaping the object emerged from its interior, sculpted by its layered structure, its residual heat, and its composition materials born in a star system with physical parameters differing profoundly from the Sun's. To the scientists mapping these anomalies, the realization grew clear. This was not simply a comet behaving oddly. This was a body built by nature around a physics shaped elsewhere. Perhaps in colder stellar nurseries where ices form in denser layers. Perhaps under prolonged exposure to cosmic rays altering chemistry deep within. Perhaps in systems with stronger stellar winds creating crusts of resilience unknown here. Perhaps shaped by tidal stresses of an exoplanetary system long since shattered. Whatever its origin, the sideways tail became a symbol of otherness, an arrow pointing toward a deeper narrative, a compass indicating not direction in space, but direction in understanding. For the tail did not merely defy the Sun, it traced the heartbeat of the object itself, and with that gesture it invited the solar system to look inward not into the tail, but into the engine behind it. The sideways tail had unsettled expectations, but it was the object's motion, its faint, almost whispered deviations across the starfields that forced scientists to confront a deeper, more intimate mystery. When Psyche, Lucy, and a handful of other deep space observers began stitching together their positional data, they noticed something so subtle that under ordinary circumstances it would have been dismissed as noise. Yet the consistency of it, quiet but persistent, revealed a pattern that could not be ignored. 3I Atlas was drifting, not dramatically, not in a way that upended orbital calculations. Its path did not veer or leap. Instead it slipped millimetre by millimetre, arc-second by arc-second, along a trajectory that gravity alone could not fully account for. It was the kind of deviation that required long hours of starfield comparison, precise motion tracking, and the resilience to question one's own assumptions. The solar system is a playground of refined motion. Every comet, asteroid, and fragment follows a path shaped by the dance of gravitational forces. Deviations happen, but they follow rules: the punch of a jet, the flicker of a rotation, the press of sunlight against asymmetric dust. These forces produce behaviors that, while intricate, remain predictable. Even the chaotic wanderings of long-period comets fit within the tapestry of Newtonian and relativistic expectations. But 3I Atlas drifted with a pattern that was not chaotic, nor was it easily described. Its deviations exhibited a soft directionality, an almost imperceptible bias. The object moved as though something inside it pulsed gently, shifting its momentum in ways too delicate to be called thrust, yet too consistent to be called randomness. Across multiple weeks of observations, the deviations formed a wave-like pattern, not smooth but rhythmic, echoing the same internal cycles seen in the ultraviolet halo and the thermal pulses detected by Sphere X. Psyche's precision measurements were among the first to suggest this. Each night, the team compared starfield snapshots aligning the object's silhouette against constellations millions of kilometers behind it. The expectation was unwavering consistency. The result was anything but. The tiny shifts, each smaller than the last joint of a human finger, when projected across astronomical distances, were nevertheless unmistakable. Lucy, observing from a nearly opposite vantage point, detected the same subtle drift, though slightly out of phase due to angle and distance. When both datasets were overlaid, the deviations matched a synchronized motion seen from two distant points in space. This was not a mistake in calibration or a quirk of instrument noise. It was real, and it hinted at layers of physics unfolding inside the object. Natural explanations emerged first, as they always must. Perhaps the drift came from asymmetric outgassing tiny jets of vapor, escaping from subsurface chambers, nudging the object in faint directional pushes. Such forces had been used to explain Oumuamua's acceleration. Yet the pattern here was different. Known jet activity produces spikes brief, intense directional, but the motion of 3I Atlas pulsed like a heartbeat. Not explosive, but continuous. Not chaotic, but textured. Some researchers proposed internal heating cycles, thermal gradients shifting gases beneath the crust, in waves producing equally wave-like changes in trajectory. Others suggested differential crust expansion, where layers warmed at uneven rates, generating micro-movements that cascaded into measurable shifts. The most intriguing hypothesis centered on layered internal structure. If the nucleus was stratified, composed of uneven densities, ancient fractures, and volatile pockets, it might respond to sunlight in ways unknown to solar system comets. The result would be subtle, periodic impulses like an alien form of thermal respiration. Each faint push would be invisible on its own, but together they would add up to the slow, drifting signature Psyche and Lucy recorded. This theory matched the broader mosaic of observations: the warm interior, the rhythmic hydrogen halo, the evolving dust shell, the sideways tail that seemed anchored to internal geometry rather than solar direction. But the deviations grew more complex. Over time, the object's drift began to show curvature, a gentle periodic bending of the path that suggested not one but multiple internal influences. It was as though the object possessed zones of varying responsiveness, each releasing material or shifting thermal load in its own cadence. The curves overlapped their interplay, crafting a finely layered tension in the object's movement. The scientific implications were immense. This was no smooth, monolithic block of ice and rock. It was something older, more weathered, more intricately shaped by environments unknown to humanity. The forces sculpting its journey were born of chemistry, structure, and history far removed from the 9 planets of the solar system. As the drift patterns became clearer, they began raising deeper questions. If the object drifted due to internal cycles, what did those cycles reveal about its past? If its trajectory evolved under forces recorded in rhythmic pulses, what ancient stellar conditions had created them? If its internal fractures vented in patterns more consistent than randomness, what story did those patterns tell? The object was not merely moving through space. It was remembering, carrying traces of its origin in the subtle shifts of its path. Researchers began to describe it not as a comet, but as a relic in motion. A relic of processes forged in the violent nurseries of stars long extinguished. Its drift, its heartbeat, its pulsations were the faint echoes of environments that no human eye had ever seen. But beneath the awe, another realization settled in. Humans were watching an object change as it traveled. Solar system bodies rarely change in observable ways over months. Their transformations are slow, geologic, almost glacial. But here was a traveller from another star evolving within the span of a single human season, a moving archive revealing its structure in real time. The drifting path, so soft, so faint, so oddly rhythmic, was not just a deviation. It was a clue, a keystone, a whispered message written in motion. This object had been shaped by forces beyond anything known in the solar system. And now, as it entered the sun's realm, those ancient forces were stirring again weakly, faintly, but undeniably. The solar system had become not just a destination, but a stage upon which the relic's old memories resurfaced. And scientists watched with growing fascination, knowing the drift was only the beginning. As the drifting pattern revealed its soft choreography, another discovery emerged. This one hidden not in motion or morphology, but in heat. Spherex, with its unparalleled sensitivity to faint thermal radiation, returned a set of observations that forced scientists to confront a possibility few had anticipated. The interstellar visitor was warm. Not warm like a silicate warmed by sunlight, not warm like a comet in early sublimation, but warm from within. The first thermal maps showed a core whose temperature surpassed expectations, by several degrees small in absolute terms, enormous in implication. At the object's current distance from the Sun, its surface should have remained locked in frigid equilibrium, too cold for significant outgassing, too distant for deep thermal penetration. Yet Spherex detected an unmistakable peak not on the surface, but radiating from under it. This was not the behaviour of dormant ice. It was the behaviour of something layered, stratified, retaining heat in pockets, insulated by a hardened crust. As the mission continued to track the object, the thermal signature did not fade or flatten, as would occur in a homogeneous ice-rock mixture. Instead, the warmth exhibited subtle fluctuations rising and falling in sync with the ultraviolet pulses MAVEN detected in the expanding hydrogen halo. A pulsating thermal core, a breathing halo, a drifting path, a sideways tail. These were not isolated anomalies. They were signatures of something structured. The idea of a layered composition took shape. Perhaps the nucleus was composed of materials with drastically different heat capacities, dense mineral regions interspersed with volatile rich ice pockets. Radiogenic materials, though rare in typical comets, could explain a small but stable heat source. So could trapped gases under pressure slowly escaping through fissures carved into the crust by ancient tidal or thermal stresses. Yet Spherex data suggested something even stranger. The thermal emission was not diffused evenly. It formed filament-like patterns, radiant stretching through the interior like glowing veins. These regions were warmer than their surroundings, as though heat travelled through channels rather than spreading uniformly. If natural, this implied a structure hardened under extraordinary forces. Perhaps the object formed near a highly energetic star with extreme radiation. Perhaps it was shaped in the debris field of a shattered exoplanet, its interior refrozen into a complex mosaic of minerals and volatiles. Perhaps its layers recorded epochs of cosmic bombardment radiation, sculpting its chemistry into unfamiliar configurations. The thermal behaviour became even more perplexing when JWST joined the analysis. Webb observed the object using its mid-infrared instrument MIRI, revealing sharply defined spectral lines, distinct peaks, that pointed to specific materials absorbing and emitting energy within the object's interior. Some corresponded to common volatiles, but others resisted classification. The wavelengths hinted at compounds formed under intense pressure, or at extremely low temperatures, materials rarely found together in solar system environments. When the Spherex and JWST datasets were combined, the implications multiplied. The core did not simply hold heat, it processed heat. It absorbed solar energy in bands, re-emitted it in others, and cycled it through internal compartments with a mechanism that was anything but random. Natural bodies absorb sunlight, none are selective about it. But 3I Atlas absorbed with intent born of composition, absorbing in wavelengths that corresponded to deep ice heating and releasing in bands associated with cooling minerals. This selective absorption suggested a mixture of volatile and refractory layers, arranged in alternating strata like geological layers pressed together over millennia of interstellar drift. In simpler terms, the object carried an internal architecture forged by environments unlike any near the Sun. Meanwhile, MRO contributed additional confirmation. The warm side of the object aligned imperfectly but noticeably with the thickest region of the dust shell. This correlation suggested that heat emerging from within was shaping the dust envelope, possibly softening the crust or triggering microvents that emitted dust in slowly shifting tides. The correlation between internal warmth dust distribution and tail deviation became harder to ignore. If the thermal core pulsed, releasing gas through semi-sealed fissures, those releases could nudge dust-shaped tails and generate microforces influencing trajectory. This explained the drifting motion Psyche and Lucy tracked. It explained the sideways tail. It matched the periodicity of the hydrogen halo expansions MAVEN recorded. But the most startling implication came from the faint thermal echoes Spherex detected behind the nucleus. In comets, warmth dissipates outward. But here, small pockets of heat appeared trailing the object cooler, but present almost like thermal residue carried in the dust. This indicated a layered crust shedding materials warmed from below, not above. The thermal wake suggested an interior venting system. Unlike anything in solar system objects, a system shaped by slow, geological or chemical processes acting over millions of years of interstellar transit. Scientists began to describe the object not as a comet, but as a fossil of a different kind of system, a relic whose internal heat carried the story of its ancient birthplace. Theories diverged. Some believed the warmth came from trapped radiogenic isotopes, materials that decayed, slowly generating heat over eons. Others suspected a deeply embedded volatile ocean, perhaps ammonia-rich or methane-rich, still reacting after its long exile from its parent star. More speculative voices suggested the object might have undergone tidal heating during its formation, suggesting it once orbited close to a massive planet or passed repeatedly through gravitational stress cycles. But whatever its origin, one truth grew inescapable. 3i Atlas was not simply warm. It was designed by nature to carry warmth, to insulate it, to channel it, to release it in rhythms. Its core held memories of a parent system, a thermal fingerprint written not by the sun but by forces long extinguished. And as the object drifted deeper into the solar system, that warmth intensified not wildly but subtly, like an ancient ember stirred by the faintest breath of starlight. The interstellar visitor was waking. As the thermal revelations unfolded, another layer of the mystery began to take shape, one woven not from heat or motion but from light. Light reflected, light absorbed, light scattered through the drifting veil surrounding the nucleus. What should have been one of the simplest properties to model brightness became one of the most confounding. Across the constellation of spacecraft 3i Atlas displayed a reflectivity that made no coherent sense, behaving like different objects, depending on the wavelength, angle and distance of observation. Lucy, positioned far from Earth, was among the first to detect the contradiction. From Lucy's vantage point, the interstellar visitor appeared surprisingly bright, too bright for its distance, an expected albedo. The reflected light carried a crispness that suggested a highly reflective surface, or unusually scattering dust grains. Yet from Earth's vicinity, using ground-based observatories, the object looked noticeably dimmer. These differences could be explained by angle or dust orientation, until Soho entered the scene. Soho, constantly gazing near the sun, registered the object as little more than a faint yellow blotch, barely distinguishable from background noise. If the object truly reflected light strongly, Soho should have caught it with far greater clarity. Yet its visible spectrum readings seemed to contradict Lucy's brightness curves entirely. Meanwhile, JWST added a new contradiction to the growing list. In infrared light, particularly in mid-IR wavelengths, the object glowed with a vivid clarity that surpassed expectations. The dust grains emitted strongly in thermal bands, yet stayed curiously subdued in visible light. Reflectance models struggled to reconcile these extremes. A surface poor at reflecting visible light should not glow so richly in the infrared, unless heated significantly, or composed of materials with highly unusual emissivity. Together, the observations painted a portrait of brightness behavior that was neither random nor trivial. It was structured a clue to composition hidden inside conflicting signals. The first hypothesis was simple extreme forward scattering. Some comets scatter sunlight strongly back toward their source, appearing brighter when observed from specific angles. But this phenomenon alone could not account for the infrared glow or the faintness recorded by Soho. Another possibility emerged: the dust grains surrounding the object could be coated with a dark carbon-rich material, common to interstellar grains. Such materials absorb visible light, efficiently producing a low albedo signature. But this explanation also fell short. Dark grains absorb, but they do not emit infrared so intensely, unless warmed internally, a condition not met by typical comets at comparable distances. Lucy's brightness readings complicated matters further. The brightness from Lucy's position remained remarkably consistent. No matter the angle of approach, no matter the rotation inferred from dust dynamics, the core's luminosity remained nearly fixed. This was not normal. Comets brighten and dim depending on which face of their rough surface rotates into sunlight. Yet 3D Atlas displayed a steadiness inconsistent with any jagged or chaotically textured nucleus. A smooth surface could create even reflection, but such a surface would be unprecedented at this scale. No comet nucleus is polished. No fragment of rock and ice launched from a distant star system should present such uniform optical behaviour, and so the contradictions grew. SOHO's faint detection, when contrasted with JWST's thermal brilliance, suggested a nucleus that was exceptionally poor at reflecting light, but highly efficient at emitting it. This implied a surface rich in low reflectivity materials, perhaps organics, carbon chains, tar-like compounds formed in cold interstellar clouds. These materials absorb light rather than reflect it, giving the object a muted visible appearance. Yet if the internal warmth detected by Sphere-X was real, this absorbed energy could be re-emitted in the infrared, explaining the object's glowing appearance in Webb's detectors. Still, something deeper tugged at the edges of the darkness. The reflectivity pattern did not behave like a typical dark body. It behaved like a composite one, with materials that absorbed visible light in some regions, scattered it intensely in others, and radiated heat in ways determined by internal structure. JWST detected subtle spectral shift signatures of minerals not typically seen in solar system comets. These materials had strong backscattering properties, reflecting light at specific angles, while remaining dim overall. The result was a brightness profile that changed so drastically with viewing geometry that it almost seemed to contradict itself. In a sense, the object wore different masks depending on where it was observed from. To unravel this, scientists modelled hypothetical grain compositions, silicate grains coated with carbonaceous shells, metallic flecks trapped in frozen volatiles, porous aggregates shaped by ancient radiation storms. None perfectly matched the observed reflectivity spectrum. The closest analogues came from laboratory studies of cosmic dust, collected in Earth's upper atmosphere grains believed to originate from outside the solar system. These grains possessed delicate filamentary structures, an extremely low albedo, yet emitted strongly in infrared bands. The match was imperfect but suggestive. If 3I Atlas was composed of similar materials, fragile, complex, carbon-rich, its brightness behaviour would be not only plausible but expected. Yet this did not explain Lucy's constant brightness readings. The answer when proposed felt almost heretical. The nucleus might be unusually spherical. A spherical nucleus, smooth, layered with a hardened crust shaped by aeons of radiation, could present a nearly uniform reflective face from multiple angles. Combined with the dust shell, such symmetry could mask rotation, flatten light curves and confuse brightness modelling. But comets from the solar system are irregular. They fracture, break, crumble. Only objects formed under intense gravitational pressure or reshaped by ancient processes achieve sustained spherical geometry. This implied origins in a system far older than the Sun, perhaps orbiting close to a massive young planet, perhaps forged in a protoplanetary disk where collisions compressed materials into hardened, rounded forms, perhaps the remnant of a once tidal-locked moon or dwarf body shattered long ago. Brightness was no longer a trivial metric. It was a message, a chemical, structural, historical message encoded in reflected and emitted light. And so the conflicting brightness became not a contradiction, but a revelation. 3I Atlas was a composite relic, an object whose visible dimness, infrared brilliance, and geometric brightness. Stability reflected an origin shaped by forces beyond the solar system's history. A relic whose very shine carried the echoes of distant stars. As the weeks unfolded and the data streams converged into an expanding mosaic, something remarkable began to happen. What once appeared to be a scattered constellation of anomalies, each strange in its own way, each troubling for its refusal to conform, began to cohere. The contradictions did not cancel each other. They completed one another. The oddities did not diverge, they aligned. The disparate signals coming from 15 spacecraft, each using different instruments, different wavelengths, different vantage points, slowly began forming the outline of something larger, something unified, Something unsettling. A pattern subtle, elegant, and deeply disturbing was emerging. It began with the thermal pulses. Spherics had detected alternating increases and decreases in internal warmth rising and falling like breath. At first the pulses seemed random, but when the timing data were cross-referenced with MAVEN's ultraviolet readings, the correlation became unmistakable. Each thermal rise coincided with an expansion in the hydrogen halo. Each cooling phase matched the halo's contraction. Two separate instruments millions of kilometers apart had chronicled the same oscillatory cycle. The object was pulsing in heat and hydrogen together. This synchronization alone was remarkable. But then Lucy's brightness curves, Psyche's trajectory drifts, and Punch's sideways tail deviations were layered atop the pattern. The pulses of heat and halo expansion aligned with slight changes in the tail's direction, the brightness's constancy, and the object's non-gravitational drift. What had seemed like unrelated anomalies were now faces of a single cycle. The visitor from the stars operated on a rhythm. The pattern repeated every few days, irregular but not chaotic. It was not precise enough to suggest machinery or control, yet not random enough to be written off as noise. It resembled what certain natural systems exhibit when they operate under internal feedback volcanic venting cycles, geyser-like releases, convection-driven thermal oscillations, or fracture-regulated sublimation. But here those processes existed not beneath kilometers of crust on an Earth-like world. They existed inside a drifting interstellar object no larger than a mountain. The rhythm was the first pillar of the emerging pattern. The second pillar came from morphology. Hubble's smooth teardrop cocoon, MRO's semicircular shell, and the dust envelope captured by Perseverance from the Martian surface were at first assumed to be independent anomalies of structure. But when researchers created 3D reconstructions using inputs from multiple spacecraft, a shape emerged that was neither accidental nor easily dismissed. The dust sheath rotated with the pulses. Moments of thermal increase correlated with thickening in the semicircular shell. Moments of thermal decrease correlated with thinning. Even the halo brightened slightly along specific arcs of the cocoon during each cycle. The dust aligned itself into a shell not because of solar wind pressure, but because of internal shifts that pushed grains outward in coordinated periodic waves. The object's morphology was breathing with its internal rhythm. The third pillar reflected composition. JWST's infrared data, SOHO's visible light faintness, and the high reflectivity detected by Lucy all hinted at a composite surface dark in visible light, efficient in infrared. When these spectra were integrated with Spherix's thermal findings, the conclusion grew firmer. The object had multiple layers of material, each responding differently to light and heat. These layers were arranged in a manner that supported the idea of a stratified, possibly geologically complex history. The brightness contradictions were not contradictions at all. They were signatures of the object's multi-layered interior. The fourth pillar, perhaps the most surprising, was motion. Psyche's starfield drift. Lucy's corroborating trajectory deviations and the slight curvature of path revealed over weeks all shared one underlying feature. Each drift spike matched a thermal halo pulse. Every pulse expelled microscopic quantities of gas-altering momentum. The forces were tiny but measurable. These microforces were not chaotic jets, but gentle, rhythmic pushes. The drifting path traced the breathing of the object. As these pillars aligned, what emerged was not a theory of artificiality. No propulsion systems, no engineered mechanisms, but a picture of startling natural complexity. A body shaped in an environment so alien that its behaviors seemed intentional, only because Earth had never encountered anything like it. This was the hallmark of true interstellar relics behavior, sculpted by physics foreign to the solar system, yet still entirely within the domain of nature. The pattern was not technological. The pattern was geological. The pattern was chemical. The pattern was ancient. The emerging picture suggested an object born in a system where extreme conditions governed the formation of icy bodies, immense pressure gradients, rapid temperature oscillations, volatile rich disks, or high radiation zones capable of baking layered shells into hardened crusts. The cycles seen today were echoes of those primordial environments, residual behavior of subsurface ices trapped beneath a crust that had spent millions of years drifting between stars. The sideways tail, the pulsing halo, the thermal veins, the bright in infrared but dim invisible surface, the drifting path, they all became chapters in the same story. A story of an object forged in violent childhood, hardened in cosmic adolescence, and now arriving in its slow senescent wanderings into the solar system, a relic carrying the memories of a star that may no longer exist. The realization was profound. This was the first time humanity watched an interstellar visitor behaving not as a frozen fossil, but as a living remnant still active, still evolving, its ancient thermal heart faintly beating after an exile longer than civilization itself. The emerging pattern was not just disturbing, it was humbling. It reminded scientists that what appeared anomalous was only anomalous because the solar system is provincial. Its environments are mild, its comets are tame. Its formation history was calm compared to the extremes possible in the galaxy. 3i Atlas was not breaking physics. It was revealing physics, and in that revelation lay a deeper truth. The universe is older, wilder, and more varied than any model born under the sun can yet imagine. As the pattern solidified, heat pulses, halo, expansions, drifting motion sideways, tail, a harder truth drifted into focus. Something at the core of cometary science began to buckle. The familiar frameworks that had guided decades of research, thermal models, sublimation, physics, dust dynamics, reflectivity thresholds, were not equipped to interpret an object shaped in a realm far beyond the solar system's radiative nursery. And so, one by one, the established theories strained under the accumulating evidence, bending under the weight of a relic forged in environments the sun had never known. The scientists did what scientists always do when confronted with the unfamiliar. They turned to models. They ran simulations, they compared analogues, they pushed their equations into extreme regimes. But as each model attempted to stabilize 3i Atlas within known parameters, each snapped apart in its own failure. One of the first models to break was thermal equilibrium. Solar system comets warm from the outside inward, their crusts heating unpredictably as sunlight triggers sublimation. But 3i Atlas warmed from the inside outward. Internal pockets heated unevenly, then radiated energy through the surface in selective infrared bands. This inverted heating pattern contradicted the fundamental principle that sunlight drives comet activity. If internal processes dominated, they had to be relics of ancient pre-exile events, long-lived radiogenic decay, trapped gases, or compression-induced energy retained since formation. Natural, yes, but profoundly foreign to solar system norms. The next model to fracture was sublimation behavior. In local comets, sublimation breaks into chaotic jets, expelling dust violently. Yet the dust shell surrounding 3i Atlas behaved like a regulated exhalation, smooth pulsating, thickening and thinning, with a coherence unmatched by any icy body observed in this system. Solar heating alone could not orchestrate such behavior. Instead, the dust responded to internal pressure waves, to layered fractures, to microvents triggered by thermal tides within the nucleus. The object was not passive, it was active, yet not in the explosive manner of comets near perihelion. It moved through cycles like a slow geological rhythm. As scientists attempted to force the behavior into jet models, the equations rebelled. The pressure gradients required would shatter an ordinary comet. The thermal lag times did not match. Dust production rates fluctuated in phase with hydrogen halo expansions, not solar input. The sublimation was not chaotic, it was choreographed by internal physics. A third model to falter was albedo prediction. A surface dark enough to be nearly invisible to SOHO should not reflect strongly from Lucy's distant vantage point. Nor should it glow with the infrared richness captured by JWST. Yet the composite reflectivity spectrum forced scientists to confront a hybrid surface layers of low, albedo organics, fused with reflective mineral grains, perhaps compressed under enormous pressure, in an exoplanetary disk perhaps shaped by gamma-ray bursts or cosmic ray sculpting over millions of years. No solar system body carries such contradictory optical signatures. But beyond the sun, in molecular clouds, in violent young star clusters, nature is capable of stranger chemistries. Next came the model most disturbing in its collapse trajectory stability. The non-gravitational drift detected by Psyche and Lucy did not match the acceleration profile seen in Oumuamua. It was too smooth, too rhythmic, too deeply tied to internal processes. Small vents could nudge a comet, but only if aligned in ways that produced chaos. Yet 3 Atlas drifted with a consistency that implied layered internal pressures, not propulsion, but structure. It was as though the object's architecture shaped how gases escaped. The deeper researchers probed, the more they realized that the object's behavior did not violate physics. It violated assumptions. Thus emerged the theories. The most conservative models pointed to a deeply stratified interstellar body, one formed in a high-radiation stellar nursery, where intense ultraviolet flux fused materials into dense crusts, while preserving volatile reservoirs beneath. Such an object could store internal heat for eons, then release it in pulses when warmed by a new star. Another model proposed tidal heating during formation. If 3I Atlas had once orbited a gas giant or binary star, gravitational flexing could have melted its interior, creating liquid layers that later refroze in complex strata. The pulsations might be remnants of this long-lost interior activity, geological echoes replayed slowly over cosmic timescales. A more exotic theory envisioned a fragment of an exomoon shattered by impact. The pressure-induced metamorphosis of such an event could produce layered silicate ice structures, dark carbon veneers, and unusual heat-retaining minerals, explaining both the object's brightness contradictions and internal warmth. But the most provocative natural model involved extreme chemistry. The presence of volatile compounds requiring temperatures far lower than typical comets to form supervolatiles like nitrogen, ice carbon monoxide ice, or even exotic clathrates would fundamentally alter sublimation behavior. Such compounds could ignite activity at distances where solar system comets remain dormant. If 3I Atlas was rich in supervolatiles, its early behavior would be expected not anomalous. And yet even these models stretched thin. The object's pulsing patterns, thermal veins, and coherent dust shell hinted not at random distributions of exotic chemistry, but at order produced by environmental forces no longer active yet preserved in structure. Thus some researchers ventured into more speculative terrain, not artificiality. There was nothing mechanical, nothing engineered about the object. But perhaps a deeper realm of natural physics was at play. Processes seen in dense exoplanetary disks where magnetic fields sculpt matter. Or conditions inside protostellar clouds where swirling pressure waves leave patterned imprints. A few voices asked, could this be a failed or incomplete planetesimal, a half-formed world that never reached equilibrium, frozen in mid-formation, carrying the signatures of a time when planets were still embryos of dust and gas? If so, then 3I Atlas was not a comet. It was a cosmic fossil frozen during birth. As these models collided, merged and evolved, one truth rose to the surface. The solar system's rules are not the galaxy's rules. Matter elsewhere follows rhythms the sun cannot teach. Chemistry elsewhere builds structures the planets have never seen. History elsewhere imprints scars the comets of our home never carry. 3I Atlas was not challenging physics. It was expanding physics. It was reminding scientists gently, rhythmically, with every thermal pulse, that the universe is not obligated to conform to the narrow range of environments humanity has studied. The theories bent, the assumptions broke, the mystery deepened, and through that deepening emerged something close to awe. As the models strained and the established theories bent under the weight of a visitor sculpted by unfamiliar physics, the scientific community found itself drifting toward a boundary. It rarely crossed the frontier where evidence ends and speculation disciplined, cautious, yet necessary begins. For mysteries of this magnitude, conjecture is not indulgence. It is an instrument, a tool for probing the edges of the known. And 3I Atlas demanded that tool for its layered structure, thermal rhythms, drifting momentum, and contradictory brightness all pointed to an origin far stranger, far older, far more complex than any solar system analogue. The object behaved not like a comet, not even like a fragment of an exoplanet, but like a relic, an artifact of natural processes that, while not artificial, bordered on the extraordinary. Scientists began to propose scenarios that stretched across interstellar distances and cosmic epochs, weaving a tapestry of potential histories for the strange visitor. The most conservative form of speculation proposed that 3I Atlas was a fragment from a rogue dwarf planet. In some young planetary systems, dwarf worlds undergo violent collisions that leave behind splintered cores and fused mantle fragments. Under intense heat and cosmic ray irradiation, such fragments can form layered crusts dark on the outside, reflective in deeper strata, rich in trapped volatiles. If such a fragment were ejected from its parent system during gravitational chaos, it could spend millions of years wandering the galaxy, accumulating a hardened skin that slowly anneals under constant bombardment. The thermal veins detected inside the object could represent relict melt channels, once molten paths that froze into crystalline conduits now carrying stored heat to the surface. Another speculative model suggested the object formed inside the deep accretion disk of a massive young star. Such environments are brutal pressure, runs high temperatures fluctuate wildly, and magnetic fields twist through the swirling dust. In this hostile nursery, grains fuse into exotic minerals, trapped volatiles become compressed in layers, and internal stresses create stratified structures. If 3i Atlas originated from such a place, its pulsations might be the lingering vestiges of internal stresses formed in an environment far more violent than the one that birthed Earth's comets. A more exotic idea posited the object as a displaced shard of an exomoon. In star systems with massive gas giants, tidal forces can stretch and compress moons, generating internal heat, akin to what occurs on Jupiter's moon Io. If such a moon shattered either through collision or gravitational disruption, its fragments would retain tidal signatures, pockets of warmth, unusual mineral mixtures and rhythmic internal stresses that might persist, even after millions of years in interstellar exile. The pulses recorded by MAVEN and SphereX could then be seen not as current processes, but as Echo's geological memory playing itself out in slow cycles. Yet even these scenarios failed to fully address the striking coherence of the object's dust shell and the oscillatory behavior of its halo. That led some researchers to propose that 3i Atlas was a transitional body, an object frozen mid-formation. In planetary systems, countless planetesimals begin to form but fail to reach planetary size. Some undergo partial differentiation, developing internal layers before ambient conditions freeze their development. If such a body were ejected early while still warm inside, it could carry a snapshot of its formation phase across interstellar distances. The layered heat signatures, the regulated outgassing, the spherical tendencies, and the composite brightness could all be artifacts of a body interrupted in the very act of becoming. There was an even stranger hypothesis, whispered only in theoretical circles, that the visitor might be a remnant of a system that experienced catastrophic stellar evolution. For example, a star transitioning into a red giant could blast its icy worlds, melting and refreezing their surfaces into hardened crusts, while leaving their interiors warm for eons. If such a system later collapsed into a white dwarf, or dispersed its planets, fragments could scatter into interstellar space, carrying within them the anomalies of their violent origin-layered mineral shells, residual heat and volatile-rich interiors, unaffected by the gentle environment around the sun. One idea dismissed publicly but entertained privately was that 3i Atlas could be a cosmic time capsule from a region near the galactic core. Their stars live fast and die violently, and radiation levels sculpt matter into exotic forms. Bodies forged in that crucible might carry properties unrecognizable to scientists accustomed to the solar system's relative tranquility. Their dust grains irradiated for billions of years could mimic the strange reflectivity patterns seen by Lucy and JWST. Their interiors, compressed during close encounters with massive stellar clusters, might retain heat in complex strata. None of these theories implied artificiality. They did not suggest intentioned design or technological origin. Rather, they acknowledged the vast diversity of natural environments that shape the galaxy environments humanity has barely glimpsed. But another form of speculation, quieter and more philosophical than scientific, began to take shape: the possibility that objects like 3i Atlas are not rare anomalies but common representatives of interstellar debris. Perhaps humanity has been shielded from this complexity simply because the universe is too large, and its encounters with such relics too few. Oumuamua had hinted at strangeness. Borisov added a second data point. Now, 3i Atlas, with its layered structure and pulsing heart, suggested that interstellar objects might not follow the modest template of solar system comets at all. Perhaps the solar system's comets are the outliers. Perhaps Earth has been studying the wrong baseline. Perhaps the galaxy is full of relics that breathe fracture pulse and drift, each shaped by its own ancient star. As these questions circulated through astrophysics conferences and private research calls, the significance of the visitor deepened. The object was no longer just an anomaly. It was a messenger, its layered physics carrying whispers of star systems. Humanity will never see its rhythmic halo, a ghostly echo of environments long lost to time, its drifting path, a signature of internal processes untouched by the sun. In this way, 3i Atlas did not simply challenge science. It expanded it. It pushed speculation to become a legitimate lens. It reminded researchers that mystery is not the enemy of understanding. Mystery is the engine that propels it. In the wake of so many anomalies, interpretations, and emerging speculative frameworks, the scientific community turned its focus toward the one question that unites every frontier of knowledge. What next? Understanding an interstellar visitor as intricate as Three-Eye Atlas required not only theories, it required tools. Instruments capable of piercing its layered crust, decoding its thermal veins, measuring its internal pulses, and tracking its gentle, persistent drift. And so, the focus shifted from interpretation to pursuit, from the meaning of the object to the method of unveiling it. Across mission centers, laboratories, observatories, and orbital platforms, researchers began coordinating a campaign of unprecedented scope. The goal was simple in concept, yet monumental in execution: to gather enough precision data to constrain the object's origin, trace its evolutionary history, and test the emerging theories about its interior dynamics and formation environment. In essence, to read the relic in the language it offered: dust, heat, motion, and light. The first instruments to intensify their surveillance were those already locked onto the visitor, the 15 spacecraft forming the solar system's accidental super-observatory. Yet soon new missions, some planned years in advance, others accelerated by the urgency of discovery, were drawn into the effort. Hubble remained a cornerstone, its sharp visual acuity continuing to map the evolving outer cocoon. Over time, it refined measurements of the teardrop envelope, capturing subtle distortions that hinted at deeper forces within. These distortions grew ever more revealing as the object neared sunlight: slight asymmetries in the shell's rim, faint shifts in dust density, delicate brightening along the arc where internal warmth pressed outward. Each distortion became a clue, a fingerprint of interior structure. But Hubble alone was insufficient. The James Webb Space Telescope, the most advanced infrared eye ever launched, became the primary instrument for spectroscopic analysis. Webb's sensors traced the object's volatile emissions with astonishing clarity, revealing changing ratios of water vapor, carbon monoxide, carbon dioxide, and unfamiliar absorption features that suggested exotic compounds. These changes were not random, they rose and fell in sync with the thermal pulses observed monthly. Webb's data became a chronicle of the visitor's internal breathing. Complementing Webb's Sphere-X prepared for additional thermal mapping, its sensors fine-tuned to detect minute variations in heat signatures. By comparing earlier scans with newer ones, Sphere-X could determine whether the object's core was growing warmer, cooling, or maintaining equilibrium. If the heat increased despite distance from the sun, the implications would ripple through every theoretical model, suggesting internal chemical reactions or even pressure-driven metamorphosis occurring in real time. Meanwhile, MAVEN expanded its ultraviolet campaign, monitoring the immense hydrogen halo for structural changes. MAVEN began searching not just for expansion and contraction, but for composition gradients, subtle shifts in hydrogen density that could reveal patterns in water dissociation rates. If the halo thickened in pulses, MAVEN could quantify the mass of volatiles being released, translating halo behavior into a measure of the object's internal reservoir. These missions formed the inner circle of scrutiny. But as the phenomenon's complexity revealed itself, new tools, some still on the ground, others in conceptual stages, were brought into the fold. The Virasi-Rubin Observatory, newly operational with its immense wide-field lens, was tasked with long-duration light curve monitoring. Rubin's specialty, detecting faint brightness fluctuations in distant targets, made it ideal for tracking the object's rotational period. If the visitor rotated even slowly, Rubin would detect the shifting shadows and altering reflectivity patterns across the dust envelope. But if brightness remained constant across all angles and nights, Rubin might confirm the strangest possibility of all: a near spherical nucleus, with uniform surface properties and unprecedented geometry for a cosmic wanderer. The European Space Agency joined the campaign with SHIOPS and Plato data pipelines, searching for spectral anomalies in starlight passing near the object's path. Though indirect, these observations could reveal dust composition through scattering patterns that Earth-based telescopes could never capture clearly. As the international effort expanded, so did the methodologies. Particle physicists adapted their models to interpret ultraviolet counts as probabilistic maps of particle density. Planetary geologists applied knowledge from icy moons and cryovolcanic bodies to simulate the stresses within a layered interstellar core. Chemists examined spectral deviations for hints of organics formed under extreme radiation, the kind expected near supernova remnants or young stellar clusters. Computational astrophysicists designed new simulation frameworks to mimic the evolution of composite interstellar bodies, tracking their internal behavior over millions of years of cosmic drift. Each discipline brought a piece of the puzzle converging on a shared objective to decode the visitor before it slipped away forever. But beyond telescopes and simulations, the most ambitious tools were still in planning. NASA began studying the feasibility of rapid response missions, small probes equipped with spectrometers, imagers and flyby cameras capable of intercepting objects like 3i Atlas within months of detection. These interstellar scouts, though not yet built, were envisioned as nimble, autonomous machines, capable of approaching an object sampling dust directly and returning high-resolution data before it disappeared into the dark. Though too late for 3i Atlas, their conception was the visitor's legacy proof that humanity required new tools to chase cosmic riddles crossing the solar system. Meanwhile, mission planners examined the possibility of leveraging existing spacecraft for a flyby. The odds were low. Orbital geometry was rarely kind. Delta-V budgets were unforgiving. Yet the mere consideration reflected the depth of scientific hunger. Even a brief flyby, even a passing snapshot at a few thousand kilometers could rewrite everything. But the window was narrow, perhaps impossibly so. Thus, observers recognized that the true laboratory was this moment, this object, this passage, this fragile alignment of machinery and cosmic timing. Everything depended on capturing the data now with the tools humanity already possessed. And so the solar system's network of observatories watched, measured, scanned, and listened. They monitored every pulse tracked, every drift mapped, every halo fluctuation. They transformed the void into a field of inquiry, turning a solitary traveller into a teacher, a messenger, a key to physics older than the sun. In a sense, the tools did more than study the object. They revealed humanity's determination to understand the universe, not just the gentle physics of home, but the wild ancient physics of exiled worlds, shattered moons, violent births, and cosmic migrations. For 3i Atlas was moving, time was short, the window was closing, and every instrument, every antenna, every lens across the solar system strained to catch the faint final whispers of a relic older than Earth itself. As the coordinated global and interplanetary effort intensified, a softer awareness settled over the scientific community, a recognition that even with 15 spacecraft watching, even with infrared eyes, ultraviolet sensors, thermal mappers, and deep space trackers, the enigma of 3i Atlas would not be unraveled completely. There was no mission ready to chase it, no probe poised to fly beside it, no instrument close enough to look beneath its hardened crust. Humanity would understand much, infer more, but never fully grasp the totality of the visitor's story. And somehow that incompleteness deepened the experience, giving the final stage of the investigation a solemn, almost reverent tone. The object continued drifting along its trajectory, carrying its layered rhythms, its pulsing thermal core, its sideways shifting tail, its softly breathing hydrogen halo. All the instruments remained focused. Webb, continuing its spectral readings, Spherex tracking the gentle heat waves rising from within, MAVEN recording the expanding and contracting ultraviolet cloud, Lucy and Psyche tracing the subtle deviations of motion, Hubble imaging the transforming shell, but beneath the mountain of data lay a deeper and more intimate truth. Science had discovered not simply an interstellar body, but a window into a cosmic narrative that transcended worlds. As the visitor approached the inner reaches of the solar system, the synergy between the spacecraft sharpened. MAVEN detected a slight increase in halo density. Webb observed a warm flicker along the interior's infrared signature. Hubble recorded a smoothing of the outer dust sheath. Psyche measured an almost imperceptible alteration in drift. These effects were tiny, nearly lost in the noise, yet unified in timing a faint crescendo in the object's ancient pulse. The solar system's machines spread across millions of kilometers caught these whispers as one. It was the closest humanity had ever come to listening to the inner workings of an object that had travelled alone through the interstellar dark for eons. In that moment, the scientific pursuit transformed into something more personal, a recognition that the visitor carried with it the memory of its birthplace of collisions and pressures, of long-vanished stars and ancient gravitational tempests. This was not simply data. It was history written in physics rather than language. Scientists gathered in virtual rooms across continents, Astrophysicists, planetary geologists, chemists, heliophysics, experts, gravitational modelers, each contributing their fragment of interpretation. Slowly, with caution and humility, a consensus began to take shape. Not a conclusion, but a narrative. Not certainty, but coherence. 3i Atlas was a relic of planetary formation, a fragment that had witnessed extreme stellar environments, survived cataclysm, drifted through interstellar desolation, and now revealed its layered secrets in the warmth of a new sun. Its behaviour was neither anomalous nor inexplicable. It was the natural expression of physics written in an unfamiliar dialect shaped by conditions that existed far from Earth's gentle cradle. Its pulses were the echoes of internal stresses frozen into place millions of years earlier. Its thermal veins were signatures of past heating events, now replaying themselves in slow motion. Its sideways tail marked the geometry of its internal fractures, a fusion of mineral and volatile layers shaping dust in ways unseen in the solar system. Its drifting path traced the faint forces of ancient trapped gases, balancing against a crust hardened by time. Its brightness contradictions recorded the mineral diversity of its place of origin, where light from an alien star sculpted materials with spectral properties foreign to the sun. Through these interpretations, one truth emerged with clarity. The visitor was not unusual. The solar system was narrow in its expectations. 3i Atlas was a reminder that the universe is vast, its nursery of worlds diverse, its methods of sculpting matter boundless. The object had not come to teach humanity anything. It had come simply because gravity had sent it here. But in passing, it allowed humans to glimpse the deeper truth of interstellar variety. And as the days grew shorter, as the object continued silently along its path and approached the limit of what current instruments could resolve, the tone of the investigation changed again. It became gentler, softer, more reflective. There would be no landing, no sampling, no probe launched in time to intercept the stranger. The visitor would pass through the solar system, revealing only the layers it chose to reveal through dust-light motion and heat, before disappearing once more into the deep indifferent dark. As the final images began to stream in, researchers felt a quiet ache, a sense of fleeting beauty. To witness such a relic, to study a wanderer forged in an alien star's embrace, was to be reminded of humanity's fragility and its persistent hunger for knowledge. The object drifted forward unconcerned with its observers, yet offering itself to science with a generosity born not of intent but of nature. And in that final movement of the visitor's passage, the narrative softened. The pace of observation eased as the object approached the limits of resolution, its once detailed shell dissolving back into the soft haze from which the first images appeared. Instruments continued to watch, but the urgency faded, replaced by a slower rhythm, a gentler cadence, as though the solar system itself were exhaling after months of attentive silence. In mission centers across Earth, scientists leaned back from their monitors, the relentless surge of data now quieting into a thinner stream, its final signatures soft and faint. The visitor drifted onward, slipping past the orbit of Mars, its cocoon shimmering faintly in sunlight, before dimming into the grey-blue of interplanetary night. Its pulses slowed, its halo thinned, its drifting path straightened as internal pressures equalized. The sideways tail softened, folding slowly into alignment with the solar wind, as the internal forces that once guided it faded gently into dormancy. Nothing dramatic announced its departure. No final burst of brightness, no sudden collapse of the shell, no last spectacle to mark the end of its passage. Instead, the object withdrew, with the same quiet grace that had marked its arrival, a subdued retreat into distance, a soft and steady fading into the dark. In the calm that followed, the scientific community found itself contemplating more than data. They reflected on distances, on time, on the fragile impermanence of encounters, measured in brief cosmic instants. They thought of stars long extinguished, of worlds shattered, of dust drifting for ages through the lonely gulf between suns. They thought of the rare privilege of witnessing a relic so old, so strange, so quietly alive, with the physics of its forgotten birthplace. And as 3i Atlas slipped beyond reach, the universe felt larger, older, and filled with more gentle mysteries than before. Sweet dreams!